Good morning, everyone. Dear chair, dear audience, let me start this session with my PhD topic, which is about novel prognostic prediction methodologies in childhood cancer. My name is Petra Varga. I'm a PhD student and a pediatric resident. My supervisor is Eszter Tuboly, and I work with Vanda Máté, Mahmoud Obeidat, Tamás Kói, and Szilvia Kisdala. I have a vision to modernize clinical care and research supporting pediatric oncology through the mission of bringing in future-proof global approaches in the risk stratification of childhood cancer. I have two specific goals. The first one is to compare the prognostic accuracy of prediction models used in childhood cancer via a systematic review and meta-analysis. Approximately 400,000 children and adolescents develop cancer worldwide each year, and even though the survival in high-income countries is already quite high, we still have some room for improvement. For example, the survival after relapse is significantly worse. Here you can see an example of acute lymphoblastic leukemia, which has otherwise a good prognosis. But in this Scandinavian study, after the first relapse, the 5-year overall survival was only around 50%. In order to determine the initial therapy of the individual patient correctly, predicting the prognosis is crucially important. In case of adults, the prognostic systems are working much better. However, in case of children, the rarity of the individual types of childhood cancer makes it really difficult to develop trustworthy prognostic models. So first, our aim was to compare the accuracy of different prediction models that are currently used in the field of pediatric oncology. We considered pediatric cancer patients with any kind of primary malignancy, and we grouped them into three categories: central nervous system and non-central nervous system tumors, and hematological malignancies. We also had three families of prediction models. In the first one, the studies used only traditional clinical factors. In the second one, they harnessed the advantage of next-generation sequencing and implemented some kind of robust genetic transcriptomic model or score. And in the third methodology, they used the same kind of data, but during the establishment of the model, some kind of artificial intelligence and machine learning method was used. Our hypothesis was that the new generation prediction models will have higher accuracy, especially the AI-based ones. We performed a systematic search at the end of 2022, and after the careful selection of the original articles and the references, we had almost 300 eligible articles. This high number of studies provided us with a lot of different primary and secondary outcomes, and we were able to do a thorough subgroup analysis as well. I will just quickly show you this forest plot. This is what I will talk about, but here I have a summary of the results you can see on that. So the gold standard of prognosis prediction is predicting the 5-year overall survival. And in our biggest forest plot, you could see it in case of, interestingly, in case of non-central nervous system solid tumor patients. Our primary outcome was the area under the receiver operating characteristic curve with the 95% confidence interval, which was in a lot of cases estimated by us. Here you can see that this is about a subgroup analysis that I was mentioning before. So here the studies were grouped based on the model category, and additionally also based on the whether the models used any kind of detail or even the outcome of treatment as a prognostic factor, and also about what kind of validation they were using, because we thought that these two factors could pose significant bias. Our most important result was that there was also a statistically significant difference between category 1 and 2 models favoring the latter. But I need to add that we have found no significant difference between category 2 and 3 models. We also found a significant difference between the validation types, namely that the external validation using studies performed significantly worse than the internal validation using ones. I think the biggest strength of our project is that we provided a broad overview of different types of childhood cancer through a high number of articles and outcomes and the detailed subgroup analysis. But we do have limitations. I would highlight the heterogeneity of patients within the groups of tumor types. So to sum up, for practice, I would highlight the importance of collaboration between clinicians and researchers, because the clinicians could help researchers significantly with standardized data collection, even on an international level. so that model building would be easier. And we also suggest the use of more modern models based on various data types in order to predict prognosis more precisely. And for research, we suggest the building of more of models using standardized quality-assured databases with a high number of patients in order to be accurate. And I would highlight the importance of model validation, since based on our results, there is a significant bias posed by internal validation, since we saw that the model performs significantly worse if it is used on a population that is different from the training one. Therefore, the model is less generalizable. And we also suggest the further exploration of AI, since I need to add that even though we found no significant difference between category 2 and 3, we found only among the 293 articles, only 37 that was about AI models. So we can conclude that AI modeling is in pediatric oncology, prognosis prediction is only in the early steps of development, but it already performs as well as the NGS-based methods that are more well established already. I have submitted my manuscript in May, and then it got transferred, so it is currently under review in eClinical Medicine. And now I would like to move on to my second project, where we plan to build a prognostic model using machine learning for childhood cancer. Based on our meta-analysis, we saw that AI models performed really well regarding the accuracy of prognosis prediction. You can see an example on the first figure. However, currently only a few studies are available in this field. One solution that we found in the literature was to train the model on adults and then validate it on children, but this way the accuracy worsens significantly. You can see that if you compare the second figure to the first one. Therefore, we think we should rather harness the data advantage of national registries. So now our aim is to build an accurate prognostic model for childhood cancer using a machine learning approach in order to help the clinical decision of risk stratification. First, we will work with the Hungarian Pediatric Oncology Network Registry, and we will have additional data sets through the BBMRI biobank catalog, and we also have an industry partner, Turbine AI. So in the Hungarian registry, we focused on neuroblastoma and central nervous system tumor patients, and we collected their clinical data, supplemented with the molecular genomic data from the Department of Pathology. And this way we had altogether 26 patients, and most of them were CNS tumor patients, so we will work with them further. Here on this map you can see the other biobanks and registries that we have already contacted and who will help us with the project, and the paperwork is currently in progress. So we finished the data retrieval and the data organization of the Hungarian registry, and the statistical analysis plan is currently in progress. We have already decided about the planned outcomes that we will predict. And in parallel, we are working on the data retrieval from the international registries, and we have also reached out to other continents, and there are some biobanks and groups who are from Canada and Australia who are interested in our research. So we are trying to have the paperwork done with them as well. To sum up, I plan to finish both of my projects this year. And my additional activities are that I am a pediatric resident doctor at the Heim National Pediatric Institute, and I have presented my work twice already at the winter meeting of the Hungarian Pediatric Oncology Network. I would like to thank you for your attention with a quote: "The difficulty lies not so much in developing new ideas as in escaping from old ones."
I have a question regarding your first project. You mentioned two types of validations, internal and external. What is about the composite that was written also?
Yes, so during the literature review, we have also found some other types of validation that we collectively called composite. These were, for example, if there was no validation done at all, or in some cases there was a validation, so there was a training set and a validation set, but for some reason they did an analysis on the whole data set and only published the results of that one. So it was really not really a validation as well. So we call these, at first we called them cheating, cheating validation, and then in order to be more professional, we call them composite.
On your first project, you showed results from the non-CNS tumors, but you showed that you measured the CNS tumors as well. Can you tell just a few words about the results of them?
Yes, actually, we think it's interesting because central nervous system tumors and hematological malignancies are much more common than non-CNS tumors, but we had very little data on CNS patients, so we could do no statistical comparisons at all. We had a few AUC values, but not a real so we couldn't have enough data to compare the model types.
What is the main difference between the genomic prediction algorithm and the AI-based algorithm? So isn't that the case that the genomic algorithms are also using AI for prediction? And also I was wondering, what are the AI model based? So what is the input?
Yes, it was. So we worked a lot on drawing the line between these two categories because the AI-based models often used the same kinds of genomic data, often mixed with clinical data. So we focused on the method that was used to determine what factors they will use for the final model, because in case of the second model category, it usually looked like they only used some kind of mathematical selection, like multivariate analysis or something like that, so that this way they could narrow down the range of the genes or RNAs that were in the final model. And in case of the AI-based ones, we have found machine learning methods like support vector machine or random forest methods, and there were a few classical AI neuronal network methods as well. So this is how we decided.
What was the data? So were there clinical variables or?
Both clinical and genomic. So I think the most common and most successful models were combining the clinical data that, for example, we have in a registry, combined with genomic data. But so the initial database that was used was the same for category 2 and 3 models. But the way they processed that data was different.
Okay, and my other question is probably I missed it because it was very quick and I couldn't understand the results. Did you do a subgroup analysis for only external validation? Because in my view, internal validation is methodologically a little bit.
Yeah. So I will go back to the table. So we did the analysis for all three kinds of validation, so the internal and external and the composite that we have asked. And yes, so the reason for this was that, yes, internal validation and especially composite validation poses a really high bias because yes, so this is why, but we found a lot of articles using these validations. So this is why we decided it's necessary to do an analysis, and our results show that it was worth it because we actually had a statistically significant difference here. But yes, we also think that this highlights the importance of external validation because that is the really objective method. Because that is when, so external validation is when the population is completely different. Internal validation often was a method like they had a population and they randomly separated them into two groups, but that's basically the same population, so it's not really a validation. We also did the risk of bias analysis that is necessary for the meta-analysis, and actually in the risk of bias tool that is used for prognostic meta-analysis, has a domain that is about these validations. So if we wouldn't have done the subgroup analysis, our study would still have the results where we show that these methods pose a significant bias. But we had so much data that we also did the subgroup analysis.
These are based on papers already published in international literature. And I mean, when you have genomic, the word genomic, it might mean quite different things and different methods. This is a quite quickly developing area of doing such prognostic analysis. How can you be ensured that the data that is derived from the different methodologies are in fact comparable?
So in case of the category 2, almost all articles they used the same methodology. Like they had the whole genome or whole transcriptome sequenced, and with some mathematical models they narrowed it down to for example, they focused on ferroptosis related genes or something like that. So they found a gene family, and they looked at those genes or RNAs and narrowed it down to the relevant prognostic factors. So for example, if like a simple genetic models, like in case of neuroblastoma, there is the MYCN gene that is a commonly used prognostic factor. So that's not really a genomic method, so we group that into category 1 as a traditional clinical method.
A bit elaborating on the previous questions and in particular on the AI methods. You already mentioned the heterogeneity, but if you kind of would describe to a general audience, I mean, you listed traditional IR random forest type, and then, for example, neural networks as another family of methods. Could you just briefly summarize these different types of methods and what types of advantages and challenges they have?
What we counted as machine learning or AI-based models, they have some kind of more advanced mathematical background, and some kind of learning can be done with them. So if you feed them some kind of data, they can find different patterns, and this is also the advantage, that they can find patterns that we humans maybe cannot find that easily. And another advantage is that they can process a really big data as well, so they can easily work with genomic and transcriptomic data, which has a lot of factors. But this is also a challenge of AI, because sometimes it finds patterns that are not relevant clinically. Because, for example, so the AI cannot surely divide between the genomic factors and because not all genomic factors have clinical relevance, because in some cases those are not even transcribed into proteins later, so it can find often irrelevant patterns as well.
Regarding the second project, would you be so kind to roll over there? And so I was keen to know that there was a number 26.
Yes, here.
So okay, and I don't know whether this is the total number of kids who had in the registry from 1974 had useful data, or
no?
What the number? What does the number mean?
Since we wanted to have the data combined, because as I mentioned previously, we think the best approach is to combine clinical and genomic data for the model. We wanted to combine them initially. Therefore, we only collected the data after 2016. the clinical data, and this is what's in the table. All the neuroblastoma and central nervous system tumor patients since 2016. Yes, after we collected the data from the Department of Pathology and combined them with the clinical data, so we matched the patients with, we have only 26 patients.
But sorry, the current pediatric oncology register do not contain histology data?
Yes, histology, yes, but not genomic data.
Okay. So, finally, what does these 26 patients mean?
That they are the ones we can work with later. So, because we want a model that combines clinical and genomic data from the Hungarian registry, these 26 patients are only useful for us.
Okay, and do you look for partners from international field?
Yes, I had, yeah.
Who has such completeness of the data of patients and with histology data as well? Okay.
Yes.
I would like to just relate to this question. So what is your target number? Because my concern is that mortality is very low, and I guess your outcome will be mortality. So like having a meaningful algorithm would require a large number of patients.
Well, we consulted with the AI team, the Turbine AI, who will help us with this part of the project, and they said that around 100 would be fine for the training. And the Princess Maxima Center actually has a lot of patients, luckily. But yes, this is why we are reaching out to other biobanks and to other continents as well. Because yes, and of course, since our meta-analysis showed that external validation is very important, if we are able to, we plan to do an external validation as well. So we need a lot of data. But here, yes, we plan on overall survival. But yeah, but I agree, maybe it's not feasible to do. So we will also focus on different other outcomes, like events, for example, or disease status as well.
And how easy is to collaborate on genomic data? I mean, like the GDPR and stuff really, I think, makes it difficult. So,
yes, my supervisor, Esther Tuboy, she's the head of the biobank here in, so the Hungarian Pediatric Oncology biobank, network biobank, and she's really an expert on these kinds of things. So she has a training in this field, also the ethical improvement and everything like that. So, but yes, it's complicated. So this is why it is currently in progress, and it's even more complicated when it's not the European Union. So Canada and Australia will also be a challenge. But I think we can figure it out.
If you could go back to the table, the first table. I just wanted to clarify one thing because I'm not sure I understood it well. Yeah, what was the difference between internal and composite validation? I know it was a question, but I think I missed the answer.
Internal validation is when they performed validation and they have a separate outcome, so a separate AUC value for both the training and validation set of patients, and the composite is, but the origin of the patients was the same population. And in case of composite validation, there was either no validation done, so only one AUC is published, or in some cases there was the training and validation from the same origin population, but they have only, but for some reason, I'm not sure why, but they have rerun the validation on the whole population set. So,
okay.
And we only had data about them.
Okay. Thank you. Now I understand. I think I don't have other questions, but I have a comment for you that might be helpful for the future. What gives shivers to the spines of statisticians is nomenclature. And AI and these methods in AI, these are very difficult, and it's a hot topic, what to call what and how to call what. So if I understood well, your definition of AI was neural networks?
Not exactly. No,
Okay.
we also use support vector machine random forest or non-negative matrix factorization. These were all considered as machine learning methods. Not
Okay, but
exactly AI, but
okay, so this is the confusion. You can
Yes.
already feel it, that we don't know what's AI, what's machine learning. And so my suggestion is to avoid confusions in future conferences where somebody will sit and say, this is not AI or this is whatever, is to avoid using these terms. Just say the name of the models and that everybody will understand it quite quickly.
okay. Thank you.
This is a very, I myself have run into this problem at a conference lately.